All right, let's dive right into this explainer. We're going to demystify exactly how you can build a highly secure, enterprise-grade, Jarvis-like AI decision platform, and do it entirely on your own local hardware. Seriously, if you've ever wanted to analyze thousands of documents, hunt down those hidden loopholes, and run really deep, stateful logic without relying on cloud APIs, well, you're absolutely in the right place. To understand exactly how we get there, here's our blueprint for today. We'll start with why standard LLMs fail, and then we'll explore the ontology paradigm shift. From there, we build out the architecture. Layer 1, the brain, Layer 2, graph memory, and Layer 3, multi-agent teams. Finally, we'll wrap up with building your local platform.
Okay, jumping into Section 1, why standard LLMs fail, and the whole problem with stateless prediction. The contrast here is pretty stark. Your standard public large language models, they're essentially just stateless text predictors. I mean, they're playing a highly sophisticated guessing game based on flat text, but true operational decision platforms, they rely on deterministic, cyclic workflows that literally never lose the plot. They aren't just generating chatty prose. They integrate structured data, they support hard decisions, and they persistently track the state of a problem from start to finish.
As the source material points out, if you just feed 10,000 pages of text to a standard AI, you're basically asking for a statistical blur. So the key takeaway here is that you really don't need to retrain some massive multi-million-dollar brain from scratch just to get better results. Actually, scratch that. What you do need is to build that existing genius brain a dedicated, ultra-organized library. That way, it never has to guess.
Moving right along to Section 2, the ontology paradigm shift, and how we actually move beyond raw text. So, to escape that guessing game, we use an ontology. And honestly, this is the true secret behind massive enterprise platforms like Palantir. Instead of just reading documents line by line, they project unstructured data onto an ontology. It creates a hard, structured digital twin of your research topic. Think of it like taking the nouns and verbs of your data, people, companies, lawsuits, regulatory changes, and explicitly mapping out their relationships. Now look at the mathematical limitation we're dealing with here. It shows exactly why flat vector search, the standard way most AI retrieves data, completely fails as your document volume grows. It's really just calculating semantic distance. Sure, that's great for a simple, single-hop lookup, but it completely lacks the ability to understand how complex facts actually connect across disparate, unrelated files. But by replacing that flat text search with an operational object layer, your data totally transforms. A competitor vulnerability or a loophole isn't just some highlighted string of text on page 40 anymore. No way. It becomes a concrete node in a database with specific properties. Things like the date it was spotted, its severity, and the specific patents it connects to.
All right, let's hit Section 3. Layer 1, the brain, and the massive power of open-weight models.
Looking at these metrics from the source material, these open-weight models are just incredible. Models like DeepSeek V4 Pro or GLM 5.1 natively use chain-of-thought loops. What does that mean? Well, it means they explicitly spend time thinking, planning their next moves, and self-correcting before they ever output an answer. And the best part? Because they're open-weight, you can run them right on your own machine. 49 billion. That is the number of active parameters DeepSeek V4 Pro uses per token. It uses what's called a mixture of experts architecture. And this is a total game changer, because it selectively activates only a subset of parameters at a time. That dramatically lowers your local compute requirements, meaning you can actually run it on a high-end workstation, all while maintaining the deep reasoning power of a trillion-parameter model. Okay, moving on to Section 4, Layer 2 graph memory, utilizing a semantic RAG pipeline.
This pipeline right here breaks down the holy grail of data engineering. It's known as Graph Retrieval Augmented Generation, or GraphRAG for short. First, a local model extracts relationships from raw text as JSON triplets, basically simple subject-verb-object connections. Then it hydrates a graph database, mapping out all the nodes and edges. Next, it uses Leiden clustering to group hidden neighborhoods of interconnected ideas into communities, and it summarizes them. Finally, you deploy a traversal agent to run global queries across all those structural paths.
And check out the long-term efficiency with this mathematical complexity scaling. While your initial ingestion scales with the total database size, the big O of n total, subsequent graph updates only scale with the new data, the delta n.
The system uses hash checks to ensure it only processes the modified files, so it keeps your localized system blazing fast even as you add more and more research over time.
Honestly, this is probably my favorite concept from the sources. Because we've separated the hard structure of the data from the processing engine, the database acts as this perfect external memory. Your AI entirely avoids the human limitation of getting tired. It completely bypasses recency bias. It's not going to forget some crucial loophole it found on page 40 just because it's currently reading page 800.
All right, Section 5, Layer 3, Multi-Agent Teams, and focusing on team orchestration.
Look, a single isolated model call just cannot solve complex analytical problems. So instead of throwing a single prompt at one AI, you define a crew AI team with explicit roles. You have a lead strategist breaking down the problem, a historical research specialist pulling past patterns, an analyst building competitor matrices, and a vulnerability assessor explicitly hunting for weak spots. You're literally forcing them to pull data, write drafts, and actively critique each other.
So what's the ultimate advantage here? It's using a framework like LangGraph to create a cyclic, stateful loop. Let's say your vulnerability assessor agent checks the logic of a drafted report and finds a loophole or a contradiction. The system doesn't just shrug and output a flawed answer. Nope. It simply routes the workflow right back to the beginning to execute a deeper, revised graph query, and it keeps doing that until the logic is absolutely flawless.
And finally, Section 6, building your local platform by deploying the open-source tech stack.
You really don't need a massive defense budget to do this. By combining these specific open-source tools like OpenFoundry for your ontology dashboards and Onyx to continuously and securely sync your local directories. Then you use VLM or XLM of V2 to run those high-parameter models in parallel. And finally, you hook up Falcor DB or Neo4j to hold your graph memory. With this stack, developers can build a private intelligence engine that rivals top-tier platforms, handling ingestion, serving, and orchestration completely offline.
This architecture empowers a single analyst to deploy a private, highly secure platform. Because the whole shebang operates locally, it scales memory limitlessly without ever exposing restricted, sensitive information to public cloud-based APIs. You own the brain, you own the memory, and you absolutely own the data.
So now that you have the complete architectural blueprint for advanced operational AI, from the semantic ontology graph all the way to cyclic multi-agent teams, the only question left is, what hidden patterns, historical connections, and structural loopholes will you unleash your localized Jarvis on first?